Might check and make sure you get audio through the phone first. And it looks like I have audio. So, we are in somewhat of this section. We talked a little bit the other day about the moments. There's some interesting approaches or mentalities for this principle of transmissibility. This is the standard form of a moment about a point. So if someone wants to know the moment about some point O, all you really have to do is draw a vector from O to the point of the application of the load and cross that with the force that's being applied somewhere. So this force is being applied at the end of this vector. That's all there is to it. The rest of it is simplifications off of math. So you can go through all of this. What you'll find out is that a lot of this stuff doesn't leave you alone. What I mean by that is this is a good case. Someone has pulling over a tree with a tractor. Draw a vector from here to here. When you have that vector, which he calls that, then what you do is you make it into a unit vector. And then what do? You multiply it times the force that the tractor is applying. Once you have that force, you did all the stuff that you had in the last chapter in order just to find the force. Now that you've done that, what's interesting is you had to have that vector of the rope, and now that vector serves two purposes. One, serves the purpose of sitting right there, and two, it was used to find the vector part of that force. You do that and you end up with the moment. This is kind of convenient because you go in here, you find out your moment is right here. This is always the case. This vector, this one and this one, produces a triangle, and perpendicular to that plane is the moment. So all of these looks incredibly similar. You simply, now what he does in the textbook is a little bit annoying to me later on, but I stick to the fundamentals. In other words, drawing a vector from the point you're interested in the moment about. You're interested in the moment about here. Draw the vector to A, where that vector runs out here. This load is applied at the end of that vector. Draw a vector out here to B. That is applied at the end of B. That's simple. Now, you go on into this, and there's a lot of sections that have some interesting simplifications. Let's go down to here. Now this is not a simplification. This is a application, if you will. This is a pretty standard looking tire iron. If you did not put your hand here as well, you are actually producing, if I drew this as a triangle, and this is a plane, this is perpendicular to all lines on that plane. But that moment there is not what is loosening the bolt. Believe it or not, what is loosening the bolt is the fact that this is the result of that twist. And in fact, this is a moment is a vector. It could be broken into two components. This one, in essence, is meaning to twist the bolt off. In other words, if you had a bolt that was sitting here, I'm not a great drawer, but you could actually twist it about this way, which would be, in this case, loosening that. But you could also try, okay, let's look down the axis. If you had the bolt sitting here, you could actually try to bend it. In other words, this is an exaggerated drawing. If you bent it, it would twist up like that. That's what this component is doing. So what is he interested in? He's interested in the useful component of what this person is doing. Meaning, in this particular case, he's trying to loosen the bolt. Remember, righty-tighty, lefty-loosey. You go on here. He's actually lefting it, or loosening it. But if you draw a vector, base vector, unit vector out here, you'll find out only the y component of that moment that's produced from this F and this R is actually useful in loosening that bolt. So what does he do? He comes up with this method by saying, I have some sort of moment. I have a direction in which I want to project that moment onto to find out what's the moment along that projected line. And so that's a pretty standard thing to do. Then there's one other component in here that's interesting. Whoops. This is a couple. Now I'm going to spend a few seconds on a couple because there's something interesting about a couple that and so that's not what I want to do. Let's here. That's reasonable. So let's just say we had a coordinate system where we drew. I'm going to show something interesting about this. We're going to have point O right here, or that's fine. So let's say we have 4 and 3, and then we pull it directly to the right. So this is our R, this is our F. Let's just make it 10I, where that's X and that's Y. Well, that one's easy to do. R is equal to 4I plus 3J. Then if you want to know the moment, you'll end up with a moment of R cross F, pretty easy. I, J, K. R be 4 and 3 and 0. F would be 10 and 0 and 0. First of all, there's only going to be a moment in the K direction. So if I just eliminate the I and J and go straight to the cofactor expansion of a K, I end up with this, 4, 3, 10, and 0. That's going to net you nothing. That's going to net you minus 30. Okay, nothing fancy there. Now, what I'm going to do is I'm going to add something to this. I'm going to say that 2 foot up, let's say these are feet, 2 foot up, we're going to add a force that goes in the absolute opposite direction of 10. So if we want to know the moment there, we already have this from the force right there. So if we want to know the moment of the other one, we draw a r vector to the point of the application load. That r would be still 4. This time it would be 3 and 2. I think that's 5. And then you use that to find the moment of, say, we'll call this F2. We'll call this one F1 now, is equal to R2 cross F2. And what you end up with is a new matrix, which in here, I'll go ahead and do this, it's a minus 10, 0, 0. And instead of a 4, well, I'm sorry, it is still a 4, but it is now a 5. Now, if you carry this out, you would get only a k component, 4, 5, minus 10, and 0. And that's going to be plus and minus, but minus and plus go together. Gives you a 50k. And that's for the moment of 2. If we're looking for the moment of both of those, the moment total is equal to this one, minus 30k, plus this one, 50k, which equals to 20k. Now, there's something interesting here. Two things that are interesting. If I go now and look at just this load by itself again, but this time I take that same, what is called couple, but I move it. So I'm going to move the couple out here. My F1 stays the same of 10i. My F2 stays the same at minus 10i. This time, I move it all the way to the point where it's 40, then say 20. So I took that couple and just moved it somewhere. But when I took it, it didn't change the distance here. Now, let's start by looking at the moment associated with this. Moment associated with 1 is R1 cross F1 equals to I, J, and K. Trying to prove a point here. The R goes out at 40, goes up to 20, 0. That's the vector that goes to right there, the point of the application of the load. The load itself is still 10. It's 0. There's only a k component, so the moment here is equal to the k component, cofactor expansion, 40, 20, 10, 0. That's 0. That's minus 200. What's interesting is, if I'm looking at these two, then they produced a different moment, but if I'm looking at the couple, let's look at the second part of this couple. That is the moment associated with 2. That would be this one. If I'm looking at that, then what I find out, just carry it out, okay? the R, the location of 2, cross the F2. Well, if I drew the R vector to right here, it's different than it was before because I moved this couple out. So I essentially took this couple and just moved it physically on the plane, but the forces remain the same. Go back into it. I get, zoom a little bit in on it. My force is still minus 10. Okay, I, J, K. So this is the force right here. The R vector is still 40. This time it's 22 and 0. This vector is the vector that originates right here, goes to there. Now, if I carry this out, that moment 2 is equal to, only a k component exists, so it's 40, 22, minus 10, and 0. Gives me a k times, that's 0. This is a minus, or 220. So moment 2 is 220. Now, if I want to know the total moment from these two forces, the moment total is equal to minus 200 k and then plus 220 k again gets you 20 k. Okay, let's look really close at this. Really close at here. And you would conclude from this that if I have a couple, in other words, took a force, say on a wheel, twisted it here, there's a twist or a couple here. If I put this on an object, say, and somebody says, what's the moment of that couple about this location? It does not matter where that is placed. It could be placed here. It could be moved here. It could be moved here. It could be moved pretty much anywhere. Anywhere that is producing the same moment about this point that all of these are. A couple is interesting that way. It basically produces a twist, but that twist remains constant no matter where it sits. If you want to see it again, you can do something interesting here. And I don't even know if I want to go down this path, but let's say I did this. Took the original drawing. So here, my original drawing sits right here. I even take this thing and now I take the couple and I turn it. So it's producing a 10, it's still 2 apart. Let's say I move it so it's 45 degrees. So anywhere I put this, so let's say this is X1, this will be Y1. This, let's assume for the moment that this is 45 degrees. So then this will be, if I zoom in here, if it is 45 degrees, then this distance and this distance are equal, and they are 2 over square root of 2. But if you do that, you just get square root of 2, square root of 2. So, in other words, if you take the square root of 2 squared plus square root of 2 squared and take the square root of it, boy, that sounds confusing, doesn't it? But that'd be 2. Anyway, let me make sure that that is correct. 2, well, we'll just go with that, 2 over square root of 2. We'll do the math. And you should be able to come in, do this. That's not going to do you any good, but let's just leave it like that. Actually, it might, but let's leave it like that. And we'll say we've got two forces, F1 and F2. Suddenly, F1 and F2 become interesting. They're a value 1, but they become minus. Okay, I may be wasting a lot of time, but I'll go ahead and write this out one more step, and then we'll just make the basic, well, maybe I should just sort of bail on this. But if I went through the math, what you're going to find out is the moment from these two couples is still going to be the distance here, and as long as this force equals that force, you've got a couple. So that's just going to give you 20. 10 and 10 and 2 apart. You can go through the math and prove no matter what angle you move it at, it's still going to give you 20. Doesn't matter where you rotate it, doesn't matter anything. So, in other words, if I took this thing, I think somehow you can rotate this thing. If I rotated it, it would still give me back the same moment. So a couple is a special version here of a moment, and it simply is as long as this and this are exactly perpendicular across here and are exactly the same, then the moment produced here is this value, or the F times the D. And most we will see later that this will be redrawn as a simple moment put there. So this would be just the moment. Well, in this case would be F times D. It's that simple. So there's a typical case. This is 30, that's 40, this is 3, that's 0.4. So that's essentially the same. So essentially, everything in these problems you look for an opposing force, a distance. This is opposing with this at that distance. This one is opposing that one at that distance. So you have actually 3 couples here. You've got, well, I don't know how to change the, here, you've got this one, you got this one, and you got this one. And that's all he does is add the 3 together. Here you've got a couple ways you could do it. If you could figure out this distance, you've got this, this, and that. And you probably could figure out that distance, but what he did is he broke it into components. You have this one and this one, forms one couple. This one and this one forms another couple. Should get the same thing. Don't think he does it the other way. So all these problems that you're seeing all have exact opposing forces some distance apart. And when you get in here, this is, I believe, one of the problems that I used. Maybe it was this one. Anyway, it was one of them. Okay, I don't know. It's not a fast machine. So here you have a couple. Okay, if you look right here, you have a couple. And if you look right here, you have a couple. And of course, you've got distances across each of these. All of these problems have that. Now, this one has an interesting component because there are no couples, but you have these written as vectors. So if you have 2 or 3 vectors, you just add them together. So if you have, of course, in this particular case, you've got a vector that comes out and forms this geometry right here. That's not that hard. You find the unit vector in this direction. You find it by using the vector to the endpoint right here. You turn it into a unit vector, you multiply it times 450, then you've got this vector. This one's pretty easy. It goes directly in the minus c direction. Same thing here. This one appears to be in the plane, basically comes out this direction. So you find the unit vector coming out here, which is a little easier than maybe that one, and then multiply it times 300, add all those up. So all these are just couples. The last thing is, well, I guess there are two last things in a group. One is a simplification of a force and a couple. For example, this is a pretty good example. In this first, these are together and these are together. This one is boring, so if you pull on the end of this, what the person feels here is that. So it's as if you took away the board and you just pulled on his hand here, assuming that's his hand, looks like his hand. This one's a little bit different. Take a long stick, put a weight at the end of the stick. This person has to not only hold that weight, but it actually has to offset the moment produced by this. In other words, if I put a 1 pound load here, you know, that 1 pound would be easy to hold. But if I put this where it was a distance 100 feet, that would be really hard to offset that moment. It would take your wrist, you would have to twist that. So when you take, and this is what he's trying to get at here, when you take a load and you move it somewhere, you have to, and you decide to move it, in this particular case, to the person's hand, you have to offset it with the moment, or include the moment due to the movement of that force. Now, if you had a couple, guess what? You don't have to have that. What I mean by that, and this is something, and maybe instead of this, let's say you're out here, and you didn't have that force, but you had a wheel, and somebody out here was doing that to it. Yeah, you could transfer each force back to it, but what he's going to feel is that there's not going to be this force, there's just going to be a moment. So when you move a force, you have to make exceptions or include the moment because you move that force. Why would you want to do that? Well, here's a good case. I think this drawing is done again in the next section, and it's a better description as to why you would want to do that. Well, it could be that it's in the next. Oh, wait a minute. Here it is. Okay, that's not it, but this is it. So in essence, when you're building this pole, I don't think he does a good job of drawing. He might do another drawing, but if not, we'll go back to that. When you are building that and bolting it to the ground, let's make sure that I'm not just dreaming. Nope, he doesn't have. So let's just use that picture. When you are building this, somewhere down here, there's a chunk of steel, and somebody's going to put a bolt here and a bolt there. Now, why would you do that? Well, why would you not just put it on like I've seen this before. You take a tire and then you just fill it with concrete here. It's heavy. I don't know if you, so in other words, this is a pretty common thing to do. You'll take this tire, old tire, and the inside of the tire sits in here like this. So what you do is fill it with concrete. It becomes heavy. You stick a pole in it. Well, that's fine. You go and do that. Have at it. What you'll find in this particular case, let's see. Let's say you did that. You filled your tire, has a concrete base. You put your pole in it, and then you put a big lamp on it. Say it's 100 pounds. 100 pounds. That's fine. You're doing great. Now, let's say the edge of this thing is, I don't know, 1 foot. So it's 1 foot here, 1 foot there, 1 foot radius, pretty much all around. Then what you do is you take your 100 pounds and you move it out here. I'm going to be extreme. 100 pounds. We're going to move it out here 1,000 feet. So it's the length of, more than the length of a football field. It's, 100 yards. That's way longer than a football field. So you're out here. What do you think is going to happen? It's just basically going to fall over. Why? Because it can't support the moment that this thing is putting on there. It can hold the 100 pounds up, but the further you move it out away from over the top of this, what you're basically doing is, if you call this a distance, then this is essentially, here, let me do it this way. This situation is essentially like putting that 100 pounds on here and then putting a huge twist on here that's essentially 100 times d. Well, this, unless it's like an infinite weight of concrete, and I don't think you can have infinite weights unless it's maybe a black hole of a concrete, then essentially this thing is just going to topple over on its side. So the moral of the story is, when you move a force, it's going to create a moment. Okay, so then you get through here. I think there was one other section that somehow I maybe have missed, or apparently I did. There was something about 2 force and 3 force members that, and that should have been back in the couple, I think, but maybe I'm wrong. Anyway, we'll run across those. So let me see about looking at the homework here. That is 7. Let's bounce it up. Look at that last problem. Oh, I'm sorry, it's the first problem. Well, let's look at this problem. So in both of these, is he supplying the same force? Looks like he is. One, he wants to know subject to the force F is determined at the moment of point A. The other one is point B. So he wants to know the moment of, in one at point A, one at point B. So that's a fairly simple problem and doesn't have anything to do with couples, but it does have something to do with moments. I'll start it, but I may not finish it. So looks to me like I'm not going to get the whole picture. Okay. So let's start with just the moment about A. All I've got to do is find that R. That R, I could list it A to C, which is probably what he's going to do in the book. So I come out 0.5, and to me, what I see is this whole thing is like a plane right here. So with that, point C has the same x distance there. Now, I clip this. The y, how far out the y did I go? I went here. To me, this goes straight down, so that means this is 0.7j. And then it looks like it drops 0.3k. And then f, which I've forgotten, was 600, 800 minus 500. 600, 800, 600, 800 minus 500. K, I, and J. So all you're doing is, that's supposed to be a C, is equal to I, J, K. I'm going to show you something with this in MATLAB in a second. 0.5, 0.7 minus 0.3, 600, 800 minus 500. I'm going to try to find MATLAB. I am going to clear it. I don't know if I cleared it. I'm going to put in the R. R, in this case, is equal to 0.5. I'm going to make them vertical. 0.5, 0.7, minus 0.3. If I'm doing it vertical, I have to do that with the force too. The force is 600, 800, minus 500. Guess what they have in MATLAB? A cross product of R, F. Now, is that the right answer? I don't know, but this is associated with the I, or the X. This is associated with the Y, or the J, and that's associated with the Z. Let me go back to this thing. This is about 0.0. Is it? I'm sorry, about point A. Minus, here, wait a minute. Get it as low as I can here. Minus 120, I'm sorry, 110, 70, and 20. It's that simple. So in fact, let's try something interesting too. Let's do this. Cross of FR. Turns out they are exact opposite of each other. So R cross F is what you do here. F cross R is not what you do. And they don't become the same thing. So you have to be careful of that. What I'm getting at is if you have two vectors, A cross B does not equal to B cross A. So be careful that R comes first and F comes second. R needs to occupy the the second row. F needs to occupy the last row, third row. So just be aware of that. So we can turn around and do this related to B, and we'll end up with a vector that originates at B and it points to C. The only thing that's different is this little 0.5. So, in other words, if you came in and you did not have this, then that would be the RB drawn to C would be 0.7J minus 0.3K. You want to find the answer there. You already have most of the stuff in MATLAB. You could say R would just be devoid of that 0.5. And then you could just simply go back and hit that. Is that the correct value? Let's go see. Minus 110, minus 180, and minus 420. So essentially you can make use of this cross, C-R-O-S-S, in MATLAB, Octave, whatever you want to use, just the same thing at this level. It's going to give you the cross product without you actually having to go through it. By the way, let's try this. I'm going to go in and say, let's say instead of doing it in that form, I did it this way. So I need to go back and look at the F where it was done. So I'm listing them as a 1 row 3 column, and you get the same answer. It just comes back to you as a row matrix with 3 columns, where the columns are I, J, and K. And so it doesn't have to be in a particular style there. So with that, I think I've got to 43 minutes here. Let's go look at anything else associated with the problem set. We did this one. I did that one already on the blackboard. So at this point we are finished with those sets, which that is 7, and 8 begins to actually pick up part of what I was talking about earlier. Okay, we need to go down to 8. 8 and 9 are together. It's a little bit slow. Okay, this moves into the next section, so I should actually talk about this before I go any further. So I think I better not go to this quite yet. So I'll draw this one to a conclusion here. This one does have a set of videos above it. So I'll call this one pretty much done.